Hello, this is a video presentation for MEC601 Final Project 1 with the title of Development of an Integrated Hydrogen Preheater and Thermoelectric Generator Waste Heat Recovery System for Hydrogen Close-Cathode Fuel Cell Mini Vehicle. My name is Muhammad Adam bin Muhammad HAMIM and I'll be the presenter, and this project is supervised by Associate Professor Dr. Wan Ahmad NAJMI bin Wan Muhammad. The project is about developing a new design for waste heat recovery system for mini hydrogen fuel cell vehicle or FCV system called integrated heat recovery or IHR, able to recover waste heat from stack to preheat supply hydrogen and at the same time utilize the waste heat to convert directly into electrical energy by using a device called thermoelectric generator. An experimental study on this system is crucial to evaluate the degree of IHR's design quality. Fuel cell vehicle, or known as FCV, is an electrical vehicle that powered by a fuel cell instead of internal combustion engine (ICE). So fuel cell itself is a hydrogen-based power generator due to electrochemical reaction between hydrogen and oxygen. So based on figure shown on the right, fuel cell consists of two plates which called anode and cathode, being separated with an electrolyte. So hydrogen as a fuel will be fed on anode side while oxygen on the cathode side. So on the anode side, positive and negatively charged particles will be split by a catalyst. So the electrolyte allows proton to pass through and move to the cathode side while blocking the electron. However, electron will flow through a circuit creating electricity and couple with photon on the cathode side. So the combination of hydrogen and oxygen producing water on the cathode side. So this is why fuel cell is broadly developed in the automotive industry, as it produces very low carbon emission or greenhouse emission and achieving energy sustainability. In this study, the type of fuel cell that will be used is proton exchange membrane fuel cell or PEMC. Close-cathode PEMC uses liquid as its cooling medium because due to endothermic reaction, heat is produced from fuel cell and thus require cooling medium. So this liquid will remove heat from fuel cell to surrounding to keep fuel cell operate at desired temperature. The operating temperature is around 50 to 100 degrees Celsius, while the overall efficiency at 40 up to 50%. So which means at maximum efficiency, the heat or thermal energy generated will be equal to the electrical energy produced. So for instance, fuel cell generating 2 kilowatt of electrical power will produce approximately 2 kilowatt of heat. So this significant amount of heat generated can be recovered for other purposes only by having a proper waste heat recovery system. So waste heat recovery is a process of recycling heat for other usage rather than release to surrounding. Since the operating temperature of PEMC is low, the heat produced is also at low temperature, considering it as low-grade heat. So due to that, it makes the heat recovery system face challenge to achieve quality result. But the most effective way to recover low-grade heat is by using thermoelectric generator or TEG. TEG is a solid-state device that used to convert directly thermal energy into electrical energy. So TEG consists of multiple coupled N-type and P-type semiconductor to allow electron flow and generate sufficient electrical potential. So according to Seebeck effect, by having a hot surface on one side and cold surface on the other side of conductive material, the temperature difference will create a potential difference across the material. So the higher the temperature gradient, the higher electrical potential will build up. And TG is very commonly used for low-grade heat application due to its simple design and having no moving parts, allowing it to conserve energy. Hydrogen acts as the fuel, plays a significant role to the performance of fuel cell. So based on study being done, power output of PEMC can be maximized by increasing the pressure of fuel. So according to ideal gas law, at constant volume and mass, increasing gas temperature will increase the pressure. Therefore, theoretically, increasing fuel cell temperature will increase its pressure. This then will increase the open circuit voltage of fuel cell and proportionally increase the maximum power output. The general efficiency of TEG approximately below 1%. To improve this value, coupling TEG with heat pipe and heat sink will definitely give positive result. Heat pipe is a passive heat transfer equipment. They are able to transfer heat at long distance with minimal heat loss. So heat sink is a feature to increase the surface area for better heat transfer rate. An experiment study shown that the efficiency of ICE or internal combustion engine increased by 1.7% with 96 TEG modules assist with heat pipe. So this TEG heat pipe and heatsink setup have potential increasing the overall TEG efficiency. CHP or combined heat and power is an application of waste heat recovery method where is a method where system provide electrical power and also thermal energy from its waste heat. So study has been done on the application of CHP for building heating, which equipped with a 5 kilowatt of PMC. So the result from this study, the CHP system able to improve the efficiency of fuel cell up to 80% while providing 68 degrees Celsius of hot water. So this has shown that by incorporate CHP in the system offer great benefits. As in for problem statement, the system is still in hypothetical stage, which limiting the existed research available. Therefore, a practical IHR system is needed as it can become reference study for future development of FCV. Issue that appear for this project is space and weight factor as it being used for mini vehicle. Thus, the overall system need to be as light and compact as possible. The first objective for the project is to develop an IHR system of liquid-cooled PEMC for mini vehicle. For this objective, the scope is to design a compact heat exchanger or CHE having high area to volume ratio and high transfer rate. CHE is target to design to increase hydrogen temperature by 50 degrees Celsius and able to recover heat by 10%. The second objective is to analyze the performance of the AG module of IHR system under various conditions. So to perform this, the test will be conducted under two different convection mode configuration, which is natural and forced convection. The flow rate of hydrogen will also vary in range of 5 to 10 liters per minute, and the TAG will place parallel with flow of hydrogen. So this variable will affect the performance of the AG module itself. Based on the project flowchart shown, it shows that all necessary tasks in respective order to conduct this project. So phase 1 in green box is designed to achieve the first objective, while phase 2 in red box construct to achieve second objective. Gantt chart for this project is also has been presented covering 2 semester timeline. So the orange signify the planned duration, while blue is for actual duration. So this is the general presentation of the IHR system. So the system includes a fuel cell stack, hydrogen supply line, liquid coolant line, electronic loader, TEG module, air supply fan, and a heat exchanger. So the fuel cell stack is connected to electronic load to simulate an actual load. So the liquid coolant line that used to carry waste heat circulating between fuel cell and heat exchanger. The hydrogen supply is first preheated through heat exchanger prior entering the fuel cell stack. Then the excess hydrogen is pushed out instead of physically back to the main supply line. TEG module is attached to heat exchanger in a position normal to the flow of ambient air, and heat exchanger will facilitate the heat transfer from hot coolant to TEG and cooler hydrogen gas. Result of theoretical analysis become the reference study for actual experimental analysis. So theoretical analysis on performance of 2.4 kilowatt close-cathode PMC can be represented by a polarization curve being shown. So based on the figure, at zero load, the open circuit voltage is at 32 volt. As the load increase up to 15 ampere, the step voltage reduced to 19 volt. So this voltage drop is primarily due to the energy being used to activate the electrochemical reaction and also due to resistance across each cell. So this is the thermal and electrical power output for pattern of the fuel cell. So as you can see, the electrical energy produced is higher compared to thermal energy in this range of current load. However, based on literature review and other research, it is expected that thermal energy generated will be greater than electrical energy at higher current load. So and this is another figure shows the effect of preheated hydrogen on its pressure and nest potential or reversible cell potential. The initial hydrogen temperature analyzed at 40 degree and final temperature at 50 degree. So for 10 degree temperature rise, the hydrogen pressure increased up to 0.66 bar. Also, the nest voltage are able to increase by 0.038%. So this small improvement is mainly due to low fuel cell operating temperature. However, for higher load, the fuel cell temperature will increase, and thus improvement on the nest potential is quite significant. So this is the thermal resistance network analysis to study the heat transfer rate between coolant through TEG and out to surrounding. So the result from this analysis enabling us to estimate the TEG electrical power output and its efficiency. However, this result still pending due to undefined parameters. So this is a conceptual design of compact heat exchanger or CHE. So the design is inspired by three figures shown, first, second and third. And the sketch on this CHE for this system in the fourth picture. So this CHE is designed to be able attaching sufficient number of TEG module in order to produce desired overall power output. So this is also a few of IHR system sketch being done throughout the study. So after performing experimental analysis on this system, it is expected to observe changes of waste heat profile for 2.4 kilowatt up to 4.8 kilowatt of fuel cell under different current load. So as the flow of hydrogen increase, the rate of heat transfer is also expected to increase proportionately. So this IR system expected to contribute at least 10% of fuel cell to fuel cell overall power output. The forced convection configuration should give better heat transfer rate across TEG and thus result in higher power output. So on this configuration also, it is expected that a single TEG able to produce at least 220 milliwatt of additional power. And overall, the IHR system need to be able to recover at least 10% of waste heat generated from fuel cell tank. So in conclusion, designing a practical IHR system definitely beneficial in terms of improving the performance of PEMC. Result from this project may become reference study for future development of fuel cell in automotive industry to achieve better energy sustainability and fuel utilization. So that's all from me. Thank you.